how to create a model that would help determine how to effectively contain the spread of Phytophthora ramorum in the Northwest. Okay, now I'm going to go through the background information I used when I did this project. What is Phytophthora ramorum, really? I mean, it sounds weird. Well, it's an aggressive water mold that attacks many plants in the Pacific Northwest, like mountain huckleberry, laurel, and many species of oaks, firs, and hemlocks. For comparison, one of its close cousins, Phytophthora infestans, caused the notorious Irish potato famines in the 1840s. Phytophthora ramorum lives in wet soil and streams up to but not deeper than 30 centimeters deep. It spreads in nature through rainwater floods and local rivers and streams. It causes a wide range of symptoms in the plants it infects, such as foliage blight and stem dieback in the top left photo, bleeding cankers in trees on the top right, and root rot, which was harder to take a picture of. Where is it? Phytophthora ramorum was discovered simultaneously in Europe and California in the early 1990s, when scientists began wondering why plants were mysteriously dying. It wasn't Stranger Things, just a water mold. In the United States, over time, the pathogen spread up the entire West Coast through the trade of contaminated nursery plants and local rivers, as shown in the map. It was also transported through infected plants to the southeast. Western Washington, which is where we are now, is now classified as a high-risk area where it is present in the wild, and eastern Washington is quickly becoming threatened as well. How do we know it's becoming so quickly? Well, we test for it. How do we test for it? Well, because the pathogen exhibits so many symptoms, it can't be detected in the field. A sample of possibly infected medium, like water, soil, or plant matter, is taken to a lab setting and allowed to grow in agar or rhododendron leaves for 2 to 3 weeks, and then checked for ramorum cultures. This allows scientists to map the spread or decline of the disease in nurseries or the wild. I'm sure you're thinking, this is all great, but why does it matter? Phytophthora ramorum is a pathogen which has the potential to damage the ecosystem of our state and national parks, and it's spreading fast. If we don't take action soon, it will become unstoppable, and that's why steaming is so important. What is steaming useful for? It kills Phytophthora ramorum and a whole bunch of other nasty guys, but it doesn't kill beneficial bacteria or seeds because they can withstand much higher temperatures than the harmful stuff. When pure ramorum is heated to 50 degrees Celsius for 30 minutes, it is killed. Steaming is fairly portable and efficient, and it uses steam generated by a boiler and transported through a hose to a plot of soil to heat the soil to the correct temperature, as shown in the bottom diagram. The top picture shows the process in action on the field at WSU Puyallup Research Center. Steaming is the best because it is the overall fastest, cheapest, and most efficient way to sterilize soil. Other options, like fumigation, concretization, and solarization, are either inefficient for large areas or harmful to the beneficial bacteria as well as pure ramorum. Yeah, steaming is pretty good, right? But how could it be made better? It could be made more accessible to nursery growers and more efficient. To make it more accessible, it would need to become more publicized as a viable option for sterilization, and it would need to be made more economically efficient. In terms of pure efficiency, an equation could be formulated to tell growers approximately how long to steam their soil to fully sterilize it. How can an equation like that be formed? Someone would need to know the major variables of the heating process. So what are they? A study published by the University of Connecticut states that soil heating profiles are changed most dramatically by surrounding air and soil moisture, as these can change the specific heat of soil the most. A steaming model would be greatly beneficial to nurseries, especially those at high risk for Phytophthora infestation. Where is Phytophthora ramorum located in nurseries? It usually hides in reused potting soil, rainwater collected to water plants, pots gathered from questionable donors, or plants brought from bad vendors, like those shown in the bottom photo. It can wipe out a whole nursery stock, depending on the nursery's cleanliness levels and types of plants. That doesn't sound too good, but what are the numbers? How much does this cost the industry in our area? According to a study from WSU Puyallup, the Phytophthora disease has infected about 50 nurseries since 2002 at an average cost of $12,000 to each nursery. This adds up to $600,000 caused in economic loss by Phytophthora alone. Nursery growers can prevent this nightmare by cleaning their nurseries regularly and watching out for diseased plants in old and new stock, especially by sterilizing their soil and other growing materials. My problem was, what is an equation researchers and businesses could use to determine how long the process of steaming will take? And my hypothesis was that an equation could be created which would accurately model the amount of time nurseries will need to steam infected plants. The independent variables I studied to perform this research were the percent moisture before steaming and the starting temperature of the soil. The dependent variable I researched was the time the soil took to reach 50 degrees Celsius plus half an hour, because that is how long it takes to kill Phytophthora remora. So how did I get the data I needed to perform my analysis? In order to collect the data, I constructed a 1 by 2 meter, 30 centimeter deep pine and cedar box to run small-scale trials. The steaming apparatus was provided by WSU Puyallup and was a SU brand steamer. I used data loggers to collect temperature information, including the soil's starting temperature and the time it took to reach 50 degrees Celsius. And I used a high accuracy scale and scientific azimuth, also provided by WSU Puyallup, to determine the percent moisture of the soil. How was my experiment prepared? My cedar box was filled with sandy loam soil, nearly identical to that used in earlier trials, and compacted effectively to ensure the soil would be the same density as it was in the ground. I dug holes in the upper left corner, center, and lower right corner, locations shown in the diagram, and took soil samples from them at the depths of 5, 15, and 30 centimeters for later use. I also inserted temperature loggers at these depths in each location to record the soil temperature throughout the heating process. The box was then prepared for steaming by laying steam hoses on the soil and covering the system with an industrial tarp, as shown in the bottom photo. How did I collect my data? I used the data loggers to collect the temperature-related variables in my equation, and the soil samples collected from each location to collect my percent moisture data. I did this by weighing out about 20 grams of soil and baking it for about 4 hours, then weighing it again and recording the percent difference in weight. These components gave me the necessary data for my equation. After I gathered my data, I began searching for correlations between the independent variables, the starting temperatures and percent moisture content, and the dependent variable, the time to reach 50 degrees Celsius, which would explain why the steaming took as long or as short as it did. I analyzed the data first by trying to perform a multivariable regression, but that didn't turn out to be a very good expression of the data. So then I tried to find correlations between the independent variables and the dependent variable individually, to find a correlation between them and the time to reach 50 degrees Celsius, and that became a much more successful approach for me. What were my results after all that work? Well, I found a positive correlation shown on the left side between the starting temperature and the time to reach 50 degrees Celsius, meaning that higher temperatures cause a longer time to reach 50 degrees. These data had an R-squared value of 0.68, which shows how well the line fits the data. An optimal value for this would be in the 0.9s, so it's not an especially good value. The correlation between percent moisture and time to 50 degrees was negative, which means that more moisture would cause a shorter length of time to reach 50 degrees. These data had an R-squared value of negative 0.537, which is 0.15 worse than the coefficient of the starting temperature data. The negative only indicates that the correlation is negative, not that it's super bad. So, as I just stated, the R-squared values were 0.68 for starting temperature and negative 0.537 for percent moisture. These matter because they show that while the starting temperature model relates better to the data, it's still not an especially good expression of the data. And if the R-squared values are low, the equations they correlate to may not be the best data expressions. The possible reason for these low depth values are the relative lack of trials, and a way to increase the R-squared value would be to conduct more trials. I wasn't that confused when I was trying to figure this out. My final equation for the predicted time to reach 50 degrees Celsius, plus a half hour allotted to fully sterilize the soil, was the predicted time equal to 3.96 0.063 minus 0.0901 times percent moisture of the plot plus starting temperature plus 1.368 plus 0.043 times the starting temperature, all divided by 2. It sounds like a crazy, terrible mouthful, but it's really just the two linear regressions from the 2 slides ago averaged for greater accuracy. The variability is shown in the bar graph in the corner. The average difference between the predicted and actual values is 0.004, which is very small and doesn't really seem to be representative of the whole population. There is one data point, third from left, which is very close, but the rest seem to vary much more widely with a maximum difference of 1.2 between the predicted and actual values. With adjustment for this discrepancy, the model can still be effective, especially because the variance is comparatively low. The model does relate directly to the cost of the steaming process. Without accounting for the purchase or rental of a SUV steamer, the cost of use is the time multiplied by the usage of gallons of gas per hour, which is 4.66, multiplied by the cost of gas, which last night in Washington was $2.07. Therefore, the highest cost in this experiment was $45.04, and the lowest was $12.06. The bar graph created by this calculation is basically identical in shape to the bar graph created by time differences. The average difference between actual and predicted gas prices was 4 cents, but the range of values was comparable to that of the time graph. These outcomes will be discussed in the conclusions of this research. What were the conclusions I drew from my research, and how will they impact the greater community? This model actually worked fairly well given the R-squared values of the 2 original linear equations, and the averaging of the 2 equations seems to have balanced the low values originally given. It has slight variability, but these differences can be rectified by simply adding an hour and a half to the predicted steaming times. Even when the times would be lower than the predicted time, it doesn't hurt the soil or beneficial organisms anymore to be at a high temperature for longer, and will only ensure the extermination of pyromorem in the soil. The results of my linear regressions are consistent with that of the data collected by Dr. Elliott at WSU Puyallup, which shows that the major statistics were correct. Also, the regressions are consistent with the expected behavior of the soil under their conditions, as water is an excellent conductor. Therefore, more water present would allow the soil to heat faster, even though the specific heat of water is very high. As an outcome of this research, I would suggest steaming to be performed in cold, wet climates. Now, on to the discussion. Some problems in this research were that most of the data was collected in fall and winter, so there was not a wide range of temperatures to experiment with. As such, the equation can't be expected to cover some of the higher temperatures that would be expected in summer. To remedy this, I would suggest that more data be collected in spring and summer to allow for a greater spread of temperatures in the original equation. Another problem was that the box was not insulated, which is seen in this photo. This was a problem because the lower layer of soil did not behave normally, heating and cooling much faster than it would have in the ground. A solution for this problem would be to wrap the sides and bottom of the box in a material that has a similar specific heat to the soil, such as pine wood. Also, the data did not behave as I expected it to, with both variables proving to have a correlation opposite to what I originally thought they would. This may be because water added to the conductivity of the soil outweighing its much higher specific heat, or a confounding variable not considered in research. Coming from these problems, what is our options for further research? Someone could perform more trials around the year in order to expand the scope of the equation. Another possibility is to use different types of soils to make equations, since most soils have different densities and specific heats. Therefore, one equation cannot be used for all of them. Alternatively, an equation could be formulated that accounts for density as a variable. The uses of this research can be extended to both business and other researchers. Nurseries can use this formula to determine how long to steam their soil, and also how much they will need to spend to use the machine itself. It also can make the process more accessible, especially to small nurseries, by showing that preventing Phytophthora outbreaks is not cost prohibitive. For researchers, it can be used as a way to determine whether their soil is behaving normally when subjected to steaming, or if their steaming is needlessly taxing their budget. Phytophthora ramorum is an urgent threat to our beautiful Washington ecosystems, and if we want to prevent the decay of our trees and forests, nursery growers, researchers, and regular people all need to work together to prevent it from spreading any further. I would like to thank my beautiful, helpful, fantastic mentor, Dr. Marianne Elliott of WSU Puyallup, Mr. DeGroat, who made sure I stayed on schedule and was prepared for everything, my Uncle Dave Hammond, who helped me construct the box, Ron and Lori Nielsen for taking us to Hawaii, and of course the amazing Green Chem class of 2017. You guys are awesome. Thanks, everyone. Now, does anyone have any questions? Yes?
Could you please repeat your hypothesis?
My hypothesis was that I would be able to create a model that was accurate to the soil samples that I had already collected. Anybody else? Yes?
What's random times random times between each trial? You could repeat all in one day without
I did it mainly in the fall, but my mentor, Dr. Elliott, provided me with data that she had taken last winter, so all of my data was from fall and winter. Yes? I think that it's possible to contain the spread at least, but it's such a infestive pathogen that it's going to be very difficult to if public opinion isn't if people aren't actually informed about the disease and told to stay clean while they go to different areas of wilderness. When people go on hikes, they may inadvertently track it from their gardens, which would spread it even more. So that's a big problem, and I think the main issue with that is that people just don't know that it's a thing. Yes?
Is there a way that we can tell just by looking at plants in the nursery whether or not they're infected?
There are some tells, like the root, foliage blight, which is just when leaves and stems off the top of the plants die, but that's an expression of many different diseases, so it's not a direct cause from Phytophthora ramorum necessarily, but it is a good indicator. Yes? I don't think they do because Phytophthora, what? Do nurseries regularly test their plants for Phytophthora ramorum was the question. So I don't think they do because Phytophthora is a controlled substance and because it's so infective and there's no protocol for regular checks in nurseries. So the only checks I've seen happen are the yearly checks, are the yearly spread detection surveys by WSU Puyallup. Anyone else?